This is lecture 35 on surface integrals of vector fields. But to start with, we describe how we would calculate the surface area, actually. Because essentially, these two problems are tied together. And so in this paragraph here, I kind of describe the setup, but I probably should give you a picture because that might help more. So essentially, to calculate the area of a surface, we can kind of think about the following approximation. So here's the surface, and so a typical point on the surface is mapped to by like the parameterization, right? Like that point would be given by, let's say, r of, I'll say uv, okay? So that's the point P, and that point right there. And then if you look at, I think I call them alpha and beta. It doesn't really matter. But if I map u, we call these u naught v naught. So that's the point u naught v naught, r of u naught v naught. So if we map u to r of u comma v naught, so fix the v naught, then that might give us a coordinate line like this, perhaps, right? And if we map v to r of u naught v, well, that might give us a coordinate line like this, right? So those are the two coordinate lines fixing one coordinate or the other. And so if I look at, for example, partial r partial u at excuse me, at u naught v naught, right? Times delta u, that will give me like a little length along, let's say, the u coordinate line, right? And likewise, partial r partial v at the point u naught v naught times delta v will give me a little length along the v coordinate line, right? And so I can kind of try to picture those, like, I don't know, like here, right? And like there, right? And technically, these, I mean, if we go in the direction of the coordinate derivations, it's not going to be exactly on the surface, but it'll be, be tangent to the surface, right? Like it gives us this little tangent parallelogram, I suppose. And if I want to calculate the area of that little parallelogram, which, by the way, has normal direction, what, n, the normal direction at u naught v naught is given by, of course, partial r partial u cross partial r partial v, evaluated at the point u naught v naught, right? But the area of that is given by the magnitude of the cross product, right? So like the area of that little parallelogram we can get by taking the absolute value right here, right? Partial r partial right here, partial r partial u cross partial r partial v, evaluate at the point, take the length of that vector, that gives you the area of the little parallelogram. And so then what you do is that gives you a pretty good approximation to the little bit of the curved surface which the shadow of this little parallelogram falls on. And you just kind of like make a grid and keep doing that, for like all over the thing, right? And so you partition the parameter domain, and you partition the, correspondingly partition the surface itself into corresponding little approximating tangent planes, right? So like I haven't pictured the parameter domains over here somewhere, right? Whatever. This is omega. I usually use omega, and so r maps omega, up to the surface. And so like, we're partitioning this with, the ui vj is like somewhere in here, like a sample point. And then that sample point maps up to a corresponding point up here, right? And then you can anchor the coordinate derivations at that point, and that will give you approximately the the side vectors, appropriate side vectors for the approximating little parallelogram there. And then so if you take the limit as the partition gets infinitely small, and then add these things up, well, that should give you a very good approximation to the surface area to that surface, right? And so that's my attempt at motivating this formula. This formula gives us a very good approximation to the surface area, and as we pass the limit m and n going to infinity, we get straight up a formula for the surface area. But of course, not being content to just say that, I've bumped it up a notch here and to find what's called the surface area integral, which integrates with respect to the surface area element. So if we put f equal to 1 here, if we put f equal to 1, then we just get the straight surface area. All right. But to calculate that, you just calculate the length of the normal vector field for the parameterization of the surface, and then integrate over the parameter domain. That gives you the surface area. And I like to think about ds as sort of its own object, if you will. It's called the infinitesimal scalar surface area element, and what you do is you take the length of the normal vector, partial r partial u cross partial r partial v, take the length of that and multiply by du dv. There you go. That's the infinitesimal scalar surface area element. You got to integrate that thing over the surface to find the surface area. So, okay, that's the first thing. Now, but then this naturally leads to calculating what's called the flux of a vector field through the surface. And so the idea of flux of a vector field through a surface is much connected, but I guess the additional wrinkle, I don't know if I got room to write it on here, but so here's like the most basic idea about flux. If you've got, this is like your area, like that, right? And if your vector field is just directly perpendicular like that, so say it's f, some constant f naught times n hat, and n hat is the normal to that surface, and this has area a, then the flux of this constant vector field through that area a is simply f naught times a. So the magnitude times the area gives you the flux. This is what flux is in its sort of most rudimentary form. And so the stronger the vector field is, as long as it's piercing the surface, the larger the flux, right? The larger the area for a given vector field, the larger the flux. If the vector field happens to be parallel to the area, then it doesn't count. So we're only going to count, so in other words, the first thing, if for constant vector fields, you could say flux is the vector field dot the area as a vector. Now area vector would be, a vector here would be like area times n hat, that would be the area vector. The magnitude of the area vector is its area, the direction is the normal to the area. So the flux is going to depend on whether you say that the area is which way is up for the area matters. So flux necessarily concerns oriented surfaces. So in any event, basically you can go through the same picture I went through just a second ago and add the wrinkle of thinking about a vector field piercing the surface, And if you think about the vector field piercing the surface, if you want to calculate the little bit of flux, in a particular, going through a particular one of these little approximating panes, well, the little bit of flux for the ij thing would just be the normal at ij, right? Dotted with the, well, it's got to be the unit normal though, right? Dotted with the vector field evaluated at that point. Sorry, it's kind of getting messy. The point is, you take the normal and you dot with the vector field. That will give you the flux of the vector field through that one. So what's going to be different is we won't just calculate the magnitude of partial r partial u. We're going to take this, in principle, divide by its length, right, and then take the dot product of that with the force field. That will give us the flux in the ijth region, and then add those all together. That gives you the flux of the vector field through the surface. Now, listen, this is the formula that I just verbalized right here. So the flux of the vector field through a surface, you take the surface, basically we take the surface integral of the normal component to the vector field. All right, this is the normal which lines up with the surface, and That's the definition of surface integral, the geometric definition, all right? But in practice, there is a nicer formula, as I derive soon after, right? F dot n hat ds, well, that n hat is n over n, as I was just talking about. And ds is the magnitude of the normal vector du dv, right? Like, I could have written up here that this is n du dv, where n equals partial r, partial u cross partial r partial v, which, by the way, as usual, is n hat, you know, by our usual rules about unit vectors. So, like, without the vector n is the magnitude. So ds is n du dv in that sense, big N. So that's what I'm doing down here. So n, the unit vector, is the normalized normal. Normalized normal. There's two different uses of normal. Sorry, I should stop this discussion. It's abnormal. I must stop. Anyway, so f dot n hat times n, this is ds, right? Then you notice that these n's cancel, and we get the like super nice, really easy to use formula. We just take the dot product of the force field with the normal vector, not normalized, just the partial r partial v, and that's the surface integral. In fact, so like pragmatically speaking, this is the formula to use, because it doesn't give any of us joy to calculate n hat for interesting surfaces. Like normalizing the normal vector field is kind of a pain. This frees you of that pain and just gives you a stone cold formula for it, which is pretty nice. And so in short, you could, in fact, and some books do, define the surface integral by this formula right here, right? So this is an alternative definition for surface integral. Alternate definition for flux. And by the way, flux of f through s, that is what the surface integral is calculating, right? And incidentally, it's nice to introduce another point of sort of shorthand notation, which is that the infinitesimal surface area, vector surface area element, ds vector, you can think of heuristically as being the partial r partial u cross partial r partial v du dv, which would be the same as n hat ds. It is not n hat ds. Oh, yes, it is. My bad. So ds vector, I'll write it over here. Ds vector is, this is straight up big N, not normalized, right? Du dv. But what is big N? Big N is the magnitude times n hat, right? Du dv, which we could also write as n hat, surface magnitude of the normal, du dv. But n magnitude normal du dv, that's exactly ds, so that's n hat ds. So that's the circle of notation here. So this heuristic is connected to that heuristic in that sense. You know, don't make too much of this. This is, in some sense, just a way of breaking down the definition, comparing two definitions and finding commonalities in their formulas. But of course, you're free to think about it more intuitively if you want. But now, anytime we make a definition in terms of a parameterization, it begs a question, a technical question, which is, does this definition depend on the choice of parameterization? Well, that would be most unfortunate if it did, because if it did, then you'd have to ask, okay, so you calculated the flux with respect to which parameterization, and that's not something we want to have to enter the fray. We want our definition of flux to be geometric, to be independent of our choice of how we parameterize the surface. And the good news is that this formula already is. The proof of that is down here. I look at a reparameterization of the surface, and this calculation, which is not something you'll see probably in 90% of Calculus 3 classes, because only an idiot like me would actually go through these details in class. I'm sorry if I'm calling you an idiot and you taught this. But anyway, through the chain rule and keeping track of the notation. Eventually, what you can see, sorting through all of it after about a page, jibber jabber, you get the relation between the normal vector in the original parameterization and the normal vector in the new parameterization. They're related by this product of this scalar function that has to do with the reparameterization functions h and g, and and when you sort through that, that's exactly the Jacobian of the change of coordinates for the parameter integral down here. So then, by the change of variables for double integrals, you get the surface area integral, the surface integral, originally written in terms of the UV parameterization, to be equal to the corresponding formula for the AB parameterization, and so that shows that it's independent of our choice of parameterization. And also, something that's not too hard to see is that if you were to reverse the orientation of the surface, then this doesn't change either. On the other hand, the surface integral for a vector field, it is dependent on the orientation, because if basically same calculation, you get this, and if the Jacobian is positive, that means that the normal vector fields will point in the same direction. Like you can see that this is the Jacobian right here. Well, I guess I've sort of, here's the formula I'm trying to talk about right here. So notice this formula right here compares the normal vector derived from one parameterization versus another, and what that says then is if this Jacobian is positive, they point in the same direction, right? So if you have an oriented surface and you want to reparameterize it, you should choose a reparameterization which maintains the orientation. Otherwise, you've picked a bogus parameterization. And so this should be positive if we're reparameterizing our oriented surface correctly. And so as such, when you, on the other hand, if that was negative, well then you'd be flipping the orientation. And so from this calculus right here, we can see then that for the surface integral, if you change the orientation, if you turn the normal upside down, then what happens is that I've got to zoom out here a bit, but I'll stay right here for now, that the integral over the surface with the normal turned upside down is equal to minus the integral with the normal turned right side up. And again, this follows from this larger discussion of how you reparameterize the integral, or just common sense. Like, this is geometrically evident because once you understand the concept of what flux is, right, and the fact that it's basically saying, okay, so like you've got this normal vector field, right, and then you think about field lines, right, and so like if the field lines for the vector field are coming through like this, if they're going like that, then that's going to give you like a positive flux, right? And so if this was for S, if I've plotted the normal field for for N for S, right? If I turn those upside down, then the red field lines, they don't change, but the dot products become minus because if the normal field points the opposite direction, then the flux becomes negative, and that's what we're seeing in this formula over here is all. Okay, so there. That's the concept of flux in short. And so what I now proceed to do is to derive the formulas for the infinitesimal surface vector surface area element, as well as the scalar surface area element, for some standard examples. And so you are free to refer to my notes. If there's an example like this in the homework, you may use these. You don't have to rework them out if you don't want to. So I'm giving you sort of a set of tools to work with here. And if you understand it, then whenever you have a problem, which is a sphere, a cylinder, a cone, a graph, a plane, one of these standard examples, then you can piggyback off my work and cut your work in half or more sometimes. But we have to understand the way this is working, right? So basically what I'm doing in example 1, you got a sphere of radius r, all right? And so how do you parameterize the sphere? Well, the easiest way to do that is to use spherical coordinates and freeze the spherical radius at r. So I just set rho equal to r, and that gives me this parameterization, like that. I calculate the partial derivatives with respect to phi and with respect to theta. I get that and that. I calculate their cross product. I get this. That simplifies into r squared sine phi rho hat. See, because this is a unit vector in the direction of increasing rho, right? And so that's r squared sine theta phi hat. And maybe it's useful to draw a picture. So if we look at a little, maybe that's the wrong shape, but you know, ds points out from that, so to speak. And it's equal to r squared sine phi d phi d rho d phi d theta, and curses, I have not left myself enough room, but I need to fit in a rho hat there. The point is the surface area element for the sphere, it points like directly out away from the sphere. That's the normal to the sphere is rho hat, right? Rho hat points out from the sphere. That's the direction of the surface area, infinitesimal surface area element right here. Right? So we can use those to calculate the surface area of a sphere, or to calculate flux of a vector field through a sphere. We can use these. Or you can refer back and use this one if you need XYZ formula, you know? Okay, so first of all, what's the area of a sphere? Well, you integrate the surface area, integrate ds, 0 to pi, 0 to 2 pi, and there you go. The surface area of a sphere is 4 pi r squared, just like that. That's pretty cool. And it's fun to notice that this is the derivative with respect to r of the volume of the sphere, right? That's kind of funny, isn't it? The same thing happens for the circle, right? Like the derivative with respect to the radius of the area of the circle is the circumference, just like the derivative of the volume is the surface area. This only happens for spheres, by the way. Try it for a cube, see what happens. Right circular cylinder. Right circular cylinder, to parameterize a right circular cylinder, what we're going to do is we're going to freeze out the radius and cylindrical coordinates at r. And that gives me the parameterization. I calculate my partial velocities, partial r, partial theta, partial r, partial z. That gives me the normal vector field r hat. Here r hat is, do I have it written anywhere? Well, I mean, find the normal vector here with respect to theta z is literally r hat, which would be r cosine theta, r sine theta, 0. So that's the way the normal field points on the sphere, not sphere, but the cylinder with this guy. Z-axis cylinder, you know. Right circular cylinder with Z as its axis, yeah. So like N is pointing out like this, you know. Alright, anyway. So that gives us ds vector is r theta d theta dz r hat, and ds is just r d theta dz. So if I want to calculate the area of a cylinder, I can integrate ds and I get 2 pi rl, which is the circumference times the length for a finite. So here I'm talking about, of course, a cylinder with a finite height from 0 to L. And this is, you know, totally unsurprising. If you took the cylinder and laid it out flat as a paper, you know, that would be, you know, take this piece of paper and we curve it. We get a, I should have found an easier thing to curl. Then we get a, you know, a cylinder. What's the surface area of the cylinder? It's that area if you just take it, and so that's the length, and then 2 pi r is how long it is, so L times 2 pi r gives me the area of the cylinder. That's what's going on here. Sorry, I was probably at not sure you could actually, I should have looked at my little viewing screen here. I was probably out of frame. Whoa, whoa, oh here. So surface area, same as if we just roll it out flat, right? This would be 2 pi r, and this would be the L. There, L. Cone. Talk about surface integrals of a cone. Well, first of all, we have to parameterize the cone, right? The parameterization of a cone is, again, easily found using spherical coordinates. We just freeze the phi angle at phi naught. So phi equal to phi naught is a cone. All right, because if here's our z-axis, right, and if we swing down angle phi naught and we go all around, well, that's a cone, right? That's a cone. And here's its parameterization. So again, I calculate the partial velocities, I take the cross product of the partial velocities, and then I remind you guys that phi hat is a vector that looks like this, and so what we have then is exactly that the normal vector field given with respect to theta and rho is rho sine phi naught phi hat, which makes sense, right? The normal vector to the cone, it ought to point in the direction of phi hat, because phi hat is the direction of increasing phi, right? So it makes sense that that's like normal. So think about how the cone sweeps down, and the phi hat should point in the normal direction for the cone, surely. So anyway, long story short, we find ds vector is rho sine phi d theta d rho phi hat, and the surface area element is just infinitesimal scalar surface area element. It's rho sine phi naught d theta d rho. And so now we can do what? Well, we can calculate the area of a cone of angle phi naught. You just get integrate the ds, and we get sine of phi naught pi r squared. Of course, this makes a lot of sense. Think about this. If the angle for the cone is pi over 2, then the cone becomes a circle, right? You ever think about that? So like this cone, if we go all the way to phi naught equals to pi over 2, right? And I'm limiting the rho from 0 to r, then the cone in this sort of exceptional case between acute and obtuse angles, right in between, the cone becomes the finite cone becomes a disk, and so this reduces. So this is like the most weird way to calculate the area of a circle I think you could think of. But anyway, next up, plane. A lot of times we want to calculate the flux with respect to a plane. And so that one's actually pretty nice. They just, parameterize the plane with 2 tangent vectors, A and B. And so then the normal vector is A cross B. And so the normal infinitesimal surface vector area element is A cross B du dv. And the scalar one is the magnitude of A cross B du dv. And in short, if we're looking at, like a plane, right? And so we, down here we've got our parameter space, whatever it is. So like, okay, so here's the plane. I'm drawing the picture down here. I can't decide which is which. Curses. I guess this is V, and this is U, let's say, and maybe my actual parameter domain is like this, omega, So that's going to give me some corresponding whatever up here, R of omega, the image up there, right? And so it turns out, if you're doing this on, if your parameterization, if your plane parameterization is nice and simple like this, what this basically says is that the area that you cover on the plane is just the magnitude of your parameterizing vectors cross product times the integral. I mean, next step here I could take would be pull that constant out, This is the constant, and then I've got the double integral of dA over omega. So for what it's worth, it would give you like area equals magnitude of A cross B times the area of your parameterization domain. So that's kind of cool. I never thought about this before. I don't think I've thought about it before. It's an interesting idea. I should think more about this. Anyway, so there you go. If you want to integrate over a plane, either calculate flux or surface area. I mean, a surface area of a plane is kind of like not something we needed special tools for already anyway. But next up, though, graph. So z equals to f of xy, many examples. In fact, some calculus textbooks pretty much just cover graphs, right? So if you have z equals f of xy, then the parameterization natural to use is xy f of xy, which gives us these partial velocities. We take the cross product of those, we get that normal vector field. We've seen this before when we were talking about the tangent plane to a graph, you might remember. And because that's the normal to that tangent plane. And so, lo and behold, here's my ds vector. And here's my formula for the surface area element. So they get the square root of 1 plus partial f partial x squared plus partial f partial y squared dx dy. And a lot of calculus books that kind of just drop this stuff in, like, that's just how you do it. And I don't know, I find that offensive. I really think that the parametric viewpoint is the correct one to take here. Otherwise, like, as a student, you just have no earthly idea why we're doing what we're doing. Maybe you still don't. I'm sorry if that's the case. If you want, I can point you to videos where I have spent an inordinate amount of time more trying to explain the basic idea. But I'm trying, but it's hard when I don't have students asking questions in real time, you know? But anyway, so the area of a graph is given by this integral. Yeah, that's kind of nice. Now here's some honest to goodness actual examples. So let's talk about these. So to calculate the total mass of a sphere of radius r which has mass density inverse tangent y over x, well that's weird. Okay, so what? Well, it's not a sphere of radius. Okay, yes, it is a sphere. I'm sorry, never mind me. Okay, fortunately you can't hear my thoughts, so the stupidity of my thoughts is my own. All right, so so the sigma is dm ds. So dm is sigma ds. If we want to calculate total mass, the thing is that this is sometimes I would call this like a spherical shell. You know, unfortunately the word sphere sometimes makes you think of solid sphere, which is what I was thinking, but this is really a spherical shell, and that's the density of the shell, so mass per unit area, like that. And so to get m, we integrate dm, which is to integrate sigma ds, so we have to integrate sigma ds over the sphere. So sigma is given to be inverse tangent of y over x, which is theta, and well, that's actually only partly true. Where is it theta, though? That's only theta for x positive, right? Let me make this problem I'm tired of thinking about this problem. The total mass of instead of a whole sphere, let's say half sphere, and let's force x to be positive, haha. And once we do that, then the angle of theta should not go from 0 to 2 pi, it should go from, like, what should it do? It should go from minus pi over 2 to pi over 2, alright? And being a little bit flippant here, ignoring the issue about what happens at pi over 2 and minus pi over 2, because technically that's not defined there, right? Um, um, let's see here. Alright, so if you allow me that abuse, then I should integrate this from minus pi over 2 to pi over 2. Oh, shnikes. Ooh, well that's 0. Huh. Huh. Whoa. Well, let me just say that you should omit this example for now. There are some issues. There are several issues. I'm sorry about that example. Let's move on. So, again, sorry about that last example. Hopefully this one will not drag us kicking and screaming into issues of coordinate defects, which I do not want to get into at this point in the semester. F of x, y, z equal to z squared over the circular cylinder. We want to calculate the average of that function. And so what you do is you divide by the area of the cylinder. I'm assuming the caps are open, so the area is just 2 pi RL. And then integrate z squared over ds. So it's a cylinder, so we can use z and theta as the parameters. So z squared is just z squared, and theta and dz, and the r d theta dz was the ds, right? ds was r d theta dz from that previous example we looked at. And so you do the integral, and you get L squared over 3. That's the average value of function over the cylinder. And then here I'm calculating the centroid of a cone. So it's like 1 over the area of the cone, integral of x ds, 1 over the area of the cone, integral of y ds, 1 over the area of the cone, z ds. This is how we calculate centroid. And so for a cone which is opening around the z-axis, I would expect that the centroid is, it's got x and y both 0, right? X bar and y bar both 0, so the interesting one is z bar. And so I used that the ds was rho over rho sine phi naught d theta d rho, but sine of pi over 2 is 1 over root 2. And so I think that's right. Yeah, sine of pi over 4 rather is 1 over root 2. And so we get this calculation right here, and that's the place where the centroid of the cone is. All right. And here I made it. I calculated the moment of inertia for the cone that's integrating r squared dm. And I got that. All right, well anyway, so these are just some sample surface integrals. I'm going to try to skip ahead here. I want to talk about the, oh fine, this is, what on earth? Oh fine, I was calculating the integral of x, y, z over an area. I was thinking this would just be a plain surface area integral, but it's not. It's integrating that density over the graph. But why don't I have a square root? Oh, because it ends up being 3 here. Fine. I said I wasn't going to do it. Let me go on. So, flux. How do you actually calculate the flux of a vector field through a surface? So I gave you the definition. Now I'm going to actually show you at least a couple of examples. So it's a pretty simple one. The vector field is constant, 1, 2, 3. I want to calculate it, the flux of it through the part of the sphere of radius 2, which is above the xy plane. So basically we're looking at the hemisphere like this, and we're trying to calculate the flux of the vector field that's above the xy plane, right? And so great, the ds vector is r squared sine phi d theta d rho hat, as we calculated. And we got z greater than 0, so there's no restriction on the polar angle. It goes all the way around. The azimuthal angle is 0 to pi over 2. We start at 0 up here, swing down to pi over 2 on the xy plane. R equals to 2 here. And so here it is. We are integrating 1, 2, 3. This is my normal vector for the spherical parameterization, and then 4, which is the r sine phi. Well, it's r squared, actually. 2 squared is 4. And so I have to take that dot product, I do it, and I get this stuff here. And since we're integrating theta from 0 to 2 pi, this is going to drop out, this is going to drop out. This is the only thing that matters. Everything else, you're integrating sine and cosine over full 2 pi, so it's going away. This, when we integrate over theta, we just pick up a 2 pi. So we should get like 6, yeah, 6. Where'd my pi go? What'd I do? 6. Well, how would I get a 6? Oh, right, I'm using trigonometry, which is that 2 cosine phi sine phi is sine 2 phi. That's what happened. I had 4 times 3, which was 12. I got rid of one of those 2's to convert to sine 2 phi. So then I get 6 sine 2 phi. Integrate from 0 to 2 pi. So that should bring me down to a 12 pi. That integrates to minus 1/2 cosine 2 phi. Evaluate from 0 to pi over 2. Well, 0 gives me 1. Pi over 2 give me pi. But, so I get minus 1/2 minus 1/2. It looks like it's going to be, what? How do I get it? What? Oh, I can't do math. This is 12 pi minus 1/2 cosine of pi plus 1/2 cosine of 0, right? So the minus of minus is a plus because cosine of pi is minus 1, right? So I get 12 pi. Which I think makes sense, right? Because if you could visualize the vector field, I mean the normal to the hemisphere is like pointing out like this, right? And the vector field that we found the flux of was the 1, 2, 3, right? So 1 over, 2 over, 3 up. So I don't know, something like this is the vector field, right? And it's like that everywhere, you know. So it makes sense that it's positive. I mean, there's going to be some, like the way it's coming in here versus the way it's going over there. It's not just the surface area times the vector field's magnitude, because it doesn't cut normally through the surface. All right. Next example, calculate the flux of this vector field, x squared plus y squared plus z squared to the n over 2 minus 1 power, x, y, z. Let's see here. So basically this formula gives me that the vector field f is rho to the power n times rho hat. Right. Well, rho hat, remember, if we want to write it in terms of x, y, z, you could write it as x, y, z divided by the length of that, right? So in view of that, yeah. I think I think this is supposed to be n minus 1 over 2. There's a typo there. because I need the minus 1/2 power on x squared plus y squared plus z squared to get this xyz over that. That is rho hat. And then that leaves me x squared plus y squared plus z squared to the n over 2, and that's rho to the n. So, yeah, there's a typo there. Sorry about that. Now, all right, so that's my parameterization, right? And so if we evaluate the vector field at the parameterization, we just get rho to the n, r to the n times rho hat. So that's kind of cool. And then so to calculate this flux integral of f dot ds, so we evaluate the vector field at the parameterization, which this time is r to the n rho hat, and then I take the dot product with the ds vector, which is rho hat r squared sine phi d theta d phi. Rho hat dot rho hat is 1, and we get r to the n plus 2, and an integral of sine phi d theta d phi. Now this integration works out to 4 pi, and so we get 4 pi r to the n plus 2, which is, you know, pretty neat, right? Now, what happens when n equals to minus 2? What happens is neat, right? And just to point out, with my typo corrected, n equals to minus 2 is the following. It's n equals to minus 2, we get minus 3 halves. So you got like xyz divided by the square root of x squared plus y squared plus z squared, all quantity cubed, right? It's that. Or if you want to write it in terms of the other notation, it's 1 over rho squared rho hat. N equals to minus 2 is the so-called Coulomb field. Coulomb field. Excuse me. Man, I need to get some more candy. That's probably my next example. So yes, as I said, n equals minus 2 is very special. In that case, the flux is independent of the radius of the sphere. The flux spreads out evenly and is neither created nor destroyed for n equals to minus 2. Now, whoa. So here I calculate the flux through a closed cylinder. I said S1, S2, S3. So to give you a picture of this, here's the closed cylinder, right? So I'm saying that the top is S1. The base down here is S2, and the side is S3. So when you have a surface like that, you need to notice that like the ds is different for here versus down here. If we usually orient surfaces so they're outward pointing oriented, right? And on the other hand, ds3, if you will, it points radially outward, right? So there are 3 different cases we have to deal with here to calculate the flux through the closed cylinder. We have to deal with the end caps differently. And so what I've done here is I've presented the parameterization for the first, the second, and the third part of the surface, and the corresponding normal vectors are this. And then I'm calculating the flux of this interesting vector field x squared z comma y. And I do that down here. And what I do is I calculate the flux through each, first of all, I take the vector field, I evaluate it the parameterization, then I take the dot product of that with the ds vector, which is this, and it ends up giving me integral of r squared sine theta d theta dr, which works out to 0, because theta integrates from 0 to 2 pi there. And a very similar calculation, I say, shows you the flux of the vector field through the other cap, through the bottom cap, is also 0. But in S3, we have to evaluate, I'll show you the details for the third one, we have to evaluate the vector field f at the parameterization, So this is r cosine theta, r sine phi z. So this is my quote-unquote x. This is my quote-unquote y. This is my quote-unquote z. So I have to plug those back into the formula for the vector field up here. So like whatever x is, I square it, put in the first one. Whatever z, I put in the middle. Whatever's y, I put in the last component. And that's what I do here. See, I take square the x component and put an x component. And then the z term I put in the y component, like I said. And the y component I put in the z term, like I. That's the formula for f. That's what f does to its inputs. All right? Because remember, f of x, y, z, by definition in this problem, is x squared z, y. So I'm just following that rule with respect to these inputs. Okay? You have to do that. That's part of thinking through the flux integral. We have to evaluate the vector field at the parameterization. And so then the ds is this, and then I take the dot product of f evaluated at the parameterization with the ds vector, and I get this, which ends up giving me an integral of cosine cubed, which is, it works out to 0. After all that, the answer is 0. Oh well. And here I have, I calculate the flux of a constant vector over a part of the plane parameterized by parameterization domain omega. And let's see here. Omega is apparently the annulus between 1 and 4, radius 1 and radius 2 in the UV plane. And so, as I said, the S vector is A cross B du dv. I take the dot product of that with my given vector C. And that's a number. I pull it out. Then I have to integrate over omega du dv. That just gives me the area of omega. But the area of an annulus, if I have outer radius 2 and inner radius 1, the area of this guy, right, it's pi times, why do I get 4? Oh, no? Oh, I'm dumb. Look, the radius, that's not 15 pi, you dummy. The radius, if u squared plus v squared is less than or equal to 4, that means that the radius for in the UV plane is going between 1 and 2. So I should have 2 squared minus 1 squared. In other words, 4 minus 1, 3 pi. Oopsie. That should be 2 squared. This should be 3 pi, right? Sorry about that. So, typo. It's not a typo, actually. It's a conceptual error. But anyway, I do make them. And then finally, here's the kind of problem you typically see in a regular, plain garden variety mainline calculus book. They tend to not talk about parameterizations hardly at all and just give you this formula for how to calculate the flux of PQR through a surface, which is a graph. And when you have a graph, you end up taking the dot product of this with the normal to the graph, which gives you this combination of terms to integrate. Minus p partial f partial x, minus q partial f partial y, plus r dx dy. And I think if you just blindly integrate this, you have no idea why this has anything to do with that geometric quantity that I described as flux. And yet that's the starting point in some calculus books. Ooh, man. Anyway, of course, yeah, here's the honest truth, is what we mean by the formula above. This is a shorthand for this is what you actually calculate. Yeah, because you have to take the p and the q and the r functions and evaluate them at the graph, right? X, y, z equal to f of x, y. And then integrate over area like that. So, and then here I actually calculate the flux for a given vector field over a, I think, paraboloid, actually. All right, so that's, I know it's kind of a long lecture, and if you don't understand surface integrals yet, there's no shame in that. It's going to take you some time. Surface integrals are not the easiest thing, but you can do them. Just take it one step at a time, and if you get stuck on something, just ask me a question, please. Thanks.